Identifying potential causes of high-frequency noise at a stage electrical system involves several key areas. Firstly, consider electromagnetic interference, or EMI, from the airport and light rail. The proximity of these facilities can generate high-frequency electromagnetic fields. These fields can induce currents in the metal roofing and other conductive elements of the building. These induced currents can manifest as noise within the ground system, directly interfering with sensitive audio equipment. Secondly, examine the possibility of ground loops. A ground loop arises when multiple ground connections inadvertently create a loop within the electrical system. This loop can facilitate the flow of current between ground points, injecting unwanted noise into the overall system. Thoroughly inspect the grounding and bonding throughout the building to identify and rectify any ground loop conditions. Thirdly, investigate for bad ground connections. An improperly connected or faulty ground connection can introduce a high impedance path for current. This high impedance can lead to the generation of noise and voltage spikes within the system. Carefully verify the continuity of all ground connections and look for any signs of damage such as loose or corroded wires, which could compromise the integrity of the ground. Once potential causes have been identified, a structured approach to investigation and troubleshooting is essential. The first step involves measuring EMI levels. Utilize a spectrum analyzer to quantify the levels of EMI present in the immediate vicinity of the ground system. Compare the measured EMI levels to establish standards applicable to performance spaces. This comparison will provide a baseline to understand the severity of the electromagnetic interference. The second step involves identifying potential ground loops. Conduct a ground loop impedance test. This test is designed to identify the presence of any loops within the electrical system. Systematically disconnect and reconnect ground connections one at a time. Observe the effect on the noise level and isolate the source of the ground loop. This process can help pinpoint the specific location of the ground loop. The third step involves carefully checking the grounding systems. Verify the overall integrity of the grounding system. This includes a thorough inspection of the ground electrodes, bonding connections, and ground straps. Conduct a ground resistance test to ensure that the grounding system meets the required resistance level as specified in the applicable electrical codes such as NEC Article 250. This ensures that the grounding system is functioning effectively. To mitigate EMI, install EMI shielding on the metal roofing or other conductive elements. This shielding will reduce the penetration of electromagnetic radiation into the building. Employ shielded twisted pair cables for audio signals. These cables minimize noise pickup along the signal path, reducing interference. Install surge suppressors or noise filters to protect audio equipment from transient voltage spikes and high-frequency noise. This protection will safeguard sensitive equipment. Further considerations must be taken into account, especially concerning the high frequency of the noise. The frequency range of 45 kHz to 88 kHz suggests a potential link to the light rail tracks. Direct current powered systems, such as light rail, are known to generate high-frequency harmonics, which could be the source of the observed noise. It is advisable to consult with an electrical engineer or an EMI specialist for further assistance. These professionals possess the expertise to diagnose and mitigate the issue effectively, especially given the complexities of the situation. Understanding the impact of electromagnetic interference, or EMI, is crucial when dealing with sensitive electronic equipment, especially in environments with significant electrical activity. EMI refers to the disturbance caused by electromagnetic radiation emitted from various sources. These sources can include radio transmitters, electrical equipment, and even natural phenomena. The effects of EMI can range from minor annoyances, such as static on a radio, to catastrophic failures of critical systems. There are several types of EMI that can affect electronic devices. Conducted EMI occurs when interference is transmitted through power lines or signal cables. Radiated EMI occurs when interference is transmitted through the air as electromagnetic waves. Understanding the different types of EMI is essential for implementing appropriate mitigation strategies. Various sources of EMI can be categorized based on their origin. Natural sources include lightning strikes, solar flares, and atmospheric disturbances. Man-made sources include radio transmitters, television stations, mobile phones, industrial equipment, and power lines. The proximity and intensity of these sources can significantly impact the level of EMI experienced. Mitigation strategies for EMI depend on the specific source and type of interference. Shielding involves enclosing electronic devices in a conductive material that blocks electromagnetic radiation. Grounding provides a low impedance path for unwanted currents to flow to ground, reducing noise and interference. Filtering uses electronic circuits to block or attenuate specific frequencies of EMI. Proper cable management involves using shielded cables and minimizing cable lengths to reduce the pickup of electromagnetic radiation. When designing electronic systems, it is essential to consider EMI from the outset. This includes selecting components that are less susceptible to EMI, implementing appropriate shielding and grounding techniques, and performing EMI testing to ensure that the system meets regulatory requirements. Ground loops are a common source of noise and interference in electronic systems. Understanding how ground loops occur and how to prevent them is essential for ensuring reliable operation. A ground loop occurs when there are multiple paths to ground in an electrical system, creating a loop. This loop can act as an antenna picking up electromagnetic radiation and introducing noise into the system. Ground loops can be caused by several factors. These factors include multiple ground connections, long cable runs, and improper grounding techniques. Identifying ground loops can be challenging, but there are several methods that can be used. These methods include visual inspection, continuity testing, and ground loop impedance testing. Once a ground loop has been identified, there are several techniques that can be used to eliminate it. These techniques include using a single-point ground, isolating ground connections, and using balanced audio cables. Using a single-point ground involves connecting all ground connections to a single point, eliminating the possibility of creating a ground loop. Isolating ground connections involves using isolation transformers or optical isolators to break the ground loop. Using balanced audio cables involves using cables with two conductors and a shield, which helps to cancel out noise and interference. Grounding systems are an essential part of any electrical system. A properly designed and installed grounding system protects equipment and personnel from electrical hazards. The purpose of a grounding system is to provide a low impedance path for fault currents to flow to ground. This allows protective devices such as circuit breakers and fuses to quickly clear the fault and prevent damage or injury. There are several types of grounding systems that can be used. These types include equipment grounding, system grounding, and earth grounding. Equipment grounding involves connecting the metal parts of electrical equipment to ground. System grounding involves grounding the neutral point of an electrical system. Earth grounding involves connecting the grounding system to the earth through a ground electrode. Ground electrodes are typically made of copper or steel and are driven into the ground. The resistance of the ground electrode should be as low as possible to ensure effective grounding. The National Electrical Code, or NEC, provides detailed requirements for grounding systems. These requirements cover the selection of grounding conductors, the installation of ground electrodes, and the bonding of metal parts. Grounding conductors must be sized according to the size of the circuit conductors. Ground electrodes must be installed in accordance with NEC Article 250.52. Bonding involves connecting metal parts together to create a continuous electrical path to ground. Regular testing of grounding systems is essential to ensure that they are functioning properly. Ground resistance testing can be used to measure the resistance of the ground electrode. Continuity testing can be used to verify the integrity of the grounding conductors and bonding connections. Electromagnetic interference, or EMI, shielding is a technique used to reduce the amount of electromagnetic radiation that enters or exits an electronic device or system. EMI shielding is essential for ensuring that electronic devices operate reliably and do not interfere with other devices. There are several methods that can be used to provide EMI shielding. These methods include using conductive materials, using magnetic materials, and using a combination of conductive and magnetic materials. Conductive materials, such as copper and aluminum, reflect electromagnetic radiation. Magnetic materials, such as ferrite, absorb electromagnetic radiation. The effectiveness of EMI shielding depends on several factors. These factors include the frequency of the electromagnetic radiation, the type of shielding material, and the thickness of the shielding material. EMI shielding can be implemented in several ways. These ways include enclosing electronic devices in a conductive enclosure, using shielded cables, and applying conductive coatings to surfaces. Shielded enclosures are typically made of metal and are designed to provide a continuous conductive path around the electronic device. Shielded cables have a conductive shield that surrounds the conductors, preventing electromagnetic radiation from entering or exiting the cable. Conductive coatings can be applied to surfaces to create a conductive barrier that blocks electromagnetic radiation. Surge suppressors are devices that protect electronic equipment from voltage spikes. Voltage spikes can be caused by several factors. These factors include lightning strikes, power surges, and switching transients. Surge suppressors work by diverting excess voltage to ground, preventing it from reaching the protected equipment. There are several types of surge suppressors that can be used. These types include metal oxide varistors, or MOVs, and silicon avalanche diodes, or SADs. Metal oxide varistors are the most common type of surge suppressor. They are inexpensive and can handle large surge currents. Silicon avalanche diodes are more expensive than MOV, but they are faster and can provide better protection against high-frequency transients. Surge suppressors should be installed at the point of entry of power into a building or facility. They should also be installed at the input of sensitive electronic equipment. Proper installation and maintenance of surge suppressors are essential for ensuring that they provide adequate protection. Noise filters are electronic circuits that are designed to attenuate or block unwanted noise signals. Noise filters are used in a wide variety of applications. These applications include audio equipment, medical devices, and industrial control systems. There are several types of noise filters that can be used. These types include low-pass filters, high-pass filters, band-pass filters, and band-stop filters. Low-pass filters allow low-frequency signals to pass through while attenuating high-frequency signals. High-pass filters allow high-frequency signals to pass through while attenuating low-frequency signals. Band-pass filters allow signals within a specific frequency range to pass through while attenuating signals outside of that range. Band-stop filters attenuate signals within a specific frequency range while allowing signals outside of that range to pass through. The selection of a noise filter depends on the specific application and the type of noise that needs to be attenuated. The high-frequency noise in the stage electrical system could be related to harmonics generated by the light rail tracks. Harmonics are multiples of the fundamental frequency of an electrical system. In a direct current system, harmonics can be generated by the switching of power electronic devices. These harmonics can propagate through the electrical system and cause noise and interference. Harmonics can be mitigated by using filters that are designed to attenuate specific harmonic frequencies. These filters are typically installed at the source of the harmonics. Consulting with an electrical engineer or EMI specialist can provide valuable insights and recommendations for addressing the high-frequency noise issue. These professionals have the expertise to conduct detailed investigations. They can perform specialized measurements and recommend appropriate mitigation strategies. They can also ensure that the electrical system meets all applicable codes and standards. The initial measurements of 45 kHz to 88 kHz at 110 mV to 180 mV between the grounds and neutral is a significant finding. These voltage levels and frequencies are indicative of a substantial noise problem that needs to be addressed. The fact that the noise is present regardless of which ground is selected suggests that the source of the noise is common to the entire grounding system. Given the proximity to the airport and light rail tracks, it is highly likely that electromagnetic interference is a significant contributing factor. The metal roofing of the building could be acting as an antenna, picking up electromagnetic radiation from these sources. This radiation can induce currents in the roofing, which can then propagate through the grounding system. A ground loop is another potential cause of the noise. Ground loops can be created by multiple ground connections that create a loop in the electrical system. This loop can act as an antenna, picking up electromagnetic radiation and introducing noise into the system. To investigate the possibility of a ground loop, it is important to check all ground connections to ensure that they are properly made. It is also important to check for any unnecessary ground connections that could be creating a loop. A bad ground connection can also cause noise in the electrical system. A bad ground connection can create a high impedance path for current, which can result in voltage drops and noise. To check for bad ground connections, it is important to verify the continuity of all ground connections. It is also important to inspect for any signs of corrosion or damage to the ground connections. To mitigate the effects of EMI, it is important to use shielded cables for all audio signals. Shielded cables have a conductive shield that surrounds the conductors, preventing electromagnetic radiation from entering or exiting the cable. It is also important to install surge suppressors and noise filters to protect the audio equipment from voltage spikes and noise. Surge suppressors divert excess voltage to ground, preventing it from reaching the protected equipment. Noise filters attenuate or block unwanted noise signals. In addition to these measures, it may be necessary to install EMI shielding on the metal roofing or other conductive elements of the building. This shielding will reduce the amount of electromagnetic radiation that enters the building. Given the complexity of the situation, it is highly recommended to consult with an electrical engineer or EMI specialist. These professionals can conduct a detailed investigation of the electrical system and recommend appropriate mitigation strategies.